Welcome to this episode of Diaspora Scholars TV. So today we are in a chemistry lab. We are at the University of Alabama in Tuscaloosa to meet Fred Motari, who's in the lab. So we are walking to the lab to meet Fred Motari. He's a student of biochemistry right here. Hey, how are you?
Good, how are you?
Yeah, good. Good to see you again.
Good to see you.
So this is the lab.
Yeah, this is the lab.
Oh, okay.
Yeah.
Oh my goodness. I hope I can greet you. In a lab there are so many rules, but
yeah, I just washed my hands.
So this is where you do your chemistry, or biochemistry.
I do my chemistry, biochemistry.
It's all still chemistry.
Yeah, it's still chemistry because you can't do my program without chemistry, and you can't do it without biochemistry. Yeah.
So you are doing a PhD in biochemistry.
In chemistry.
In chemistry.
Yeah.
But your research is more biochemistry based.
More biochemistry based.
Oh wow!
Right.
Excellent.
Yeah.
So tell us a little bit of what we are seeing here.
Okay. This is Dr. Phantom Lab.
Plantom.
Yeah, Patrick Phantom.
Patrick Phantom.
Yeah, is my PI. So I'm doing more into glycosyl transferases, and the rest of my group is doing the self-cluster enzymes.
So basically, it's a lab that deals with enzymes involved in metabolism.
In metabolism, you're right. So soon I'm moving to start with the self-cluster enzymes because this is the grant that we receive here is supported by the self-cluster enzymes.
Okay.
Yeah.
Okay. Maybe spare us the details, but but broadly speaking, for the viewers of us who are not chemists, why do you even study those enzymes? Why do you have to do that?
Okay. Just to make it for the viewers to understand, to design the drugs. We need to understand how the enzymes function. Okay. The enzymes of the bacteria and the human enzymes. Yeah. So to derive the drugs and the inhibitors, that's the drugs in terms of the inhibitors, we need to understand how enzymes work.
Because there are many drugs which inhibit certain enzymes.
Yeah.
Okay. So it's mostly also understanding more about applicability in drug development and things like those.
Yeah, sure. So that's why we are basically looking at this in this lab to understand how the enzymes work. We do the mutations of these enzymes and understand how they work. Then from there, they can be used to design the drugs.
Oh, okay.
Yeah.
So, tell us a little bit, what am I looking at, for example? What is this instrument? This is, I see, UV visible sticker. Very briefly, in simple words, for the sake of our viewers, because they'll wonder, you are doing a PhD in chemistry, it's a mystery to some people.
Sure.
Then there are people who really want to do what you are doing, but simplify it for us so that people are motivated to come and do chemistry in the University of Alabama in Tuscaloosa. For example, what does this instrument do?
Okay. I can say this is almost a final step instrument because this is for the assays, whereby we do the kinetic assays and look at the kinetic parameters of an enzyme, the Michaelis Menten parameters, and see how the enzyme functions. But basically, to make it procedural, the first thing that we do can start from here in a quick way. So this is the incubator. This is where we incubate our cells and leave them for some time to grow and they express the protein.
Okay, so this is where you do the bacterial culture.
Yeah, the culture. Then to allow the protein expression, depending on the type of protein, it can take 16, 18, 3 hours, 5 hours, depending on the type of protein that we are trying to express. Okay. Then from there, we have the sonicator here. This one is to lyase the cells. Okay. So that to break the bacterial cell walls.
So once you have made the bacterial culture, now you come here to break it open.
Yeah, to break it open.
To release the proteins you want.
To release the proteins we want. So basically there are other steps in between, like centrifugation, to centrifuge the cells and get the pellets. Then we lyase the pellets here to get the cells, the protein from the cells. Okay. Then from there, we take it back to the centrifuge. This one here. So this one has a loader that we keep in the fridge, in the fridge. Then we fix it, and then we centrifuge our cells at maximum speed. And then from there we get the pellets and the supernatant. We get the supernatant, and then we take.
So your protein will be in the supernatant, or simply will be the one on top layer.
On top, yeah. Then the cells will be at the bottom. Depending on the protein you are working, if it's the first time or not, you can dispose them or retain them. Then from there, we use this. This is our FPLC, the fast protein liquid chromatography. Yeah.
Oh yeah. So you have the name FPLC right here.
It's a very expensive.
So, So this is for separating purifying the protein.
Yeah, it's a very automatic machine because you don't sit here moving tube by tube to get your protein.
I tell you, that's what I did in graduate school. I used to literally, we had an old one who I would change tubes one by one.
Yeah, that's what I was doing in my master's program.
Oh my, that's tedious.
Yeah, it was tedious.
It's not a fancy machine like this.
No, it's millions of dollars.
Yeah, and I see you are able to see your peaks.
Yeah, you are able to see.
So when you see such a peak, you know that's your protein.
Your protein is here now.
Yeah.
So then you do the SDS page on this. You can start from here up to here. Then you see where exactly your protein lies from the SDS chromatogram. So
I like the setup because this one you don't have to be in the cold room.
No.
I remember when we were doing this, we used to sit in the cold room because the instrument was in the 4 degrees room.
It has to be in the 4 degrees.
But at least this one you are working from outside and you are able to control it.
You work from outside, you open it, put your buffers here, set your columns here, and if you open it for long,
the temperature will start beeping. Wow, nice setup.
Once you set it up, then it's a very nice machine. Then this is the size exclusion chromatogram, and this one is good for separating the proteins to further purify them for crystallography.
Oh wow! Yeah. Oh, you even go further to do exclusion.
To do crystallography because you need to understand how these proteins function after you do the mutations to form the variants.
Oh yeah. Oh wow! And then after that you still have to do find out whether the enzyme is even active.
Yeah, you have to come and do the kinetic parameters here and see how the enzyme functions. If it's dead, living,
that's a disappointment.
If it's dead after doing a mutation, maybe you'll say, "Oh, I cracked something." It means
because that can also mean something.
Yeah, it's important. It means this type of residue is important for the protein
function.
Yeah. So it can lead to something. So
that is true.
This is where we do the kinetic parameters. This is the UVVC spectrophotometer. So we have 2 of them, and this one is good for the number of members we have here in the research group.
So how many people work in this lab?
Currently we are currently we are 4 of us, and 1 is out, but 2 are out, but they will be coming soon. They took a break for some few months because of personal matters, but we are 6 in number.
6 in number.
Yeah.
And the name of the professor again?
Is Dr. Patrick Fandom.
Patrick Fandom.
Yeah.
So if people go to the website, they can be able to see, of course, the work that you people do.
Yeah.
Oh, wonderful, amazing. So are you the only Kenyan in this lab?
Yeah, in this lab, I'm the only Kenyan. Other students, we have students from Asia and 1 from Africa.
Which country is that?
We have one student from Ghana.
Oh, so there's a Ghanaian and then you are Kenyan.
Yeah, there is 1 from India and 1 from Nepal. Another 1 from Sri Lanka. And then 1 is an American student.
So out of 6, only 1 is American.
Yeah.
And the other 5 are international
students.
That's why we do this, folks. This is the Diaspora Scholars TV. This is a lab where we have 6 PhD students, 5 of whom are all in the diaspora. And one of them, of course, is Fred Motari, who's gearing to get his PhD.
Yeah, you're right.
You'll get it. Yeah, it's just a matter of time.
It's time.
How long have you been here now in this lab?
So I came here in the summer of 2023, So I joined the lab in the fall of 2023. Actually, the end of fall 23. Specifically, I can say it's the spring of 2024.
Oh, spring of 2024.
Yeah, that's when I started working here. Yeah.
So 2024. Now this is 2025. We're already in, in almost in summertime.
Yeah.
You've already gotten a feel and the hang of this lab for sure.
Yeah, it has been good because I managed to get some good data, and I did a poster.
Oh, you did a poster
in Atlanta.
Which conference was that?
It was the Southeast Enzyme Conference. It was in Georgia this time, Atlanta.
Oh, nice, excellent. We look out for that again next time. And I mean, guys are doing amazing work. And when you were talking, I was looking at that board over there. Cameraman Fred, you wanna look at this this chart over here, because it reminds me of there's a TV show. there's a TV show. I don't know whether you know it, where we have a Sheldon, the Big Bang Theory. Your favorite program, where we have those PhD with similar looking whiteboards with lots of formulas and equations. I'm telling you, this is good stuff. This is PhD.
This is where we spend the time with our professor. This is where he guides us on what to do. Where we get stuck, he explains the mechanisms behind it or the theory behind it, and then we are able to proceed with the experiments.
Wow.
Yeah.
Wow.
So this is the other group dealing with the South system.
And it's making sense.
Yeah.
Folks, this is stuff that is done by a human being. Of course, if you're a biochemist, this is easy for you. To some people, it may look Greek or junk, but no, it's done by real people, real Kenyans, like Fred Motari, and also other students who are in this lab. Another one is from Ghana, India, Nepal. They are here. 5 out of 6 students are all diaspora scholars right in the University of Alabama in Tuscaloosa.
Yeah.
You'll make it, my friend.
Thank you.
How good is my data? So over here, the examples of...
How good is the data? So this is a motivation from the previous students on what they were doing. How good is the data? And it guides us on if you have good data, the best graphs, how they look like.
What to aim for example, this was a mutation.
Yeah, this is a mutation.
R to 119 to A. So R was mutated to residue 119. Was registered.
So this is arginine that was mutated to alanine.
Okay.
So if you look at this,
alanine to cysteine.
The data is not.
It's all over the place.
All over the place. And if you look at the far end, you realize that the data it fits well.
Pristine. Wow.
Fits with the line of it, and then the curve looks good on that. So
the catalytic activity is good.
Yeah.
Wow, excellent. So anyway, so folks, again, this was part 2 of the story of Fred Motari, who works in this lab. You can always reach out to him by going to the University of Tuscaloosa. You know the name of the professor again?
Dr. Patrick Frandom.
Patrick Frandom.
Patrick Frandom. Yeah.
We'll also put a link of Fred Motari on this video. Subscribe to this video as well to enable us also be able to reach other scholars like him. If you want to reach out to him and support him, do so again via this channel. And also subscribe. My name is Daktari. See you in the final part of Fred Motari's story. Bwana,